Last Thursday and Tuesday we talked about size scales of things in the universe. How big is a planet? How big is a star? How big is a galaxy? How big is the universe? Today we're going to talk about time scales in the universe. So rather than asking ourselves how big things are, we're going to ask ourselves how long they take. And this is useful because the lifespan of a human being is what, roughly 100 years? And yet most things in the universe take place on a time scale of billions of years. So we can't really wait around for everything to happen in order to figure it out. So we talked about the sizes of objects and the distances between them. So as a nice little example of that, let's take the sun and squish it down to the size of a basketball. So it's this big in my hands. And the question is, if the sun is that size, how far away will the planets be from it? So the first thing we can see that if we take something as immense as the sun, we make it that small, even with that rate of compression, 5 billion times smaller than its natural size, we still can't fit the Earth in this building. To find the Earth, we got to run across the parking lot to my office, and the Earth is sitting on my desk in a little cup. If you don't believe me, go check. Pluto, the planet furthest from the sun, and I'm going to keep calling it a planet for now, is out in the campus observatory. So that's across the street, 1 block down, 1 block down, 1 block over. Pretty far. That's how far it is, and it's very, very small. So you can go down there and check it out, but you might step on it without realizing it. The nearest star is in Hawaii. That's how big the distance is between stars. So that means that if you were to look out on the plane, the disk of our galaxy, you would see a basketball, and then you would have to travel 8,000 miles in our scale model in order to find the next basketball. And everything in between would be negligible, almost nothing. So that should give you an idea of the vast emptiness of space. That was fun, but now let's make it even smaller. This basketball is too heavy. So let's take the sun, bring it down again. Another factor of 10. Now we got a marble in my hand. So we can fit the Earth in the classroom now. Randy has the Earth in his pocket, a couple rows back. Pluto is now in the Zoo Library, and that is the size scale of our own solar system. If you put a marble here, all of the planets fill themselves in roughly in the distance between a couple of buildings on campus. The nearest star, that's in Pueblo. And the center of our own galaxy, just our own galaxy, that is 10 times further away than the moon. So that would tell you, if you sparsely littered the area between us and the moon and 10 times further with a few marbles and grains of salt, that's what the solar system is like. Nearest galaxy, that's on Mars. Anybody remember the name of that nearest big galaxy? Good, that's Andromeda. So Andromeda is where Mars is to us. And remember, Mars is a planet roughly as big as the Earth, and yet it's so far away that in the sky it looks like a tiny bulb of light. So the point here is to give you a fun sort of example of how the solar system scales, and how not just space very, very far away from us is mostly empty, but our own solar system is pretty empty as well. You could drive around there without a map for days without finding any planet. And that's why this whole miracle of sending the rovers to Mars is so impressive. Because in effect, we shot something off blind in our own atmosphere, and we managed to make it to the next planet. And now with your newfound appreciation for just how much empty space there was there, it's not like you could just pull into another planet, pull into a gas station on the way and get an update on your directions. This is a really hard problem. Okay, so that's our solar system. And now we're going to talk about the speed of light. But I've already said this. So a quick recap. The speed of light is constant. I told you that this is why very distant objects, we see them not as they are today, but as they were in the past, because it takes time for the light from them to come here. So in theory, this is a very Star Trek idea, but if we had a mirror Earth and a planet just like the Earth, very far away, and if we had an unrealistically accurate telescope that could actually see small things on it, if we looked at that in the past, we could actually observe the dinosaurs on it, because we wouldn't see it as it is today. We would see it millions or billions of years ago. So that is why we say a telescope is like a time machine. More distant objects takes longer for the light to get to us, and so we see them as they were in the past. What does someone see at the other side of the universe training the telescopes back on us, on our Milky Way galaxy? Dinosaurs, yeah. Or, they may not, they don't have the fine resolution, but they see our galaxy not as it is today, but as it was in the past. So this isn't just a game that we play. It's a game that astronomers all over the universe are playing simultaneously. That's a neat trick. I'd like to see the historians come up with anything nearly as good. So now we're going to go through a list of objects. So this is very similar to the exercise we did with distances, only now we're looking at timescales. So we have a list of timescales, and I've given you some things that I hope you all know, like the amount of time it takes the Earth to go once around the sun, and some timescales that are going to take some thinking, like how long does it take for a star to die, and what is the average lifetime of a star? How long does it take light to travel from the sun to the nearest star? So we've got a large number of timescales here, and we're again going to break them into groups because that makes the problem easier. So let's start with the 4 shortest timescales. Time for the Earth to go once around the Sun, time for planet Jupiter to go once around the Sun, the time that it takes light from the nearest star to travel to the Sun, and the time it takes light to travel from the Earth to the Sun. We're going to break in discussion groups of roughly 5 and go ahead and sort these from shortest to longest. Then if you get through with that, estimate the rough length of each one. What do we think? We've got the time for the Earth to go around the Sun, also known as... Excellent. It's like being an orchestra conductor up here. Jupiter, the amount of time it takes Jupiter, a planet which is further away from the Sun, has a larger orbit. It's 5.2 times further away. The amount of time it takes light to get from the nearest star, and the amount of time it takes light to get from the Sun to the Earth. So everyone knows that the Earth goes around the Sun in a year. Anyone have any idea how long it takes Jupiter to go around the Sun? Roughly 10 years. Yeah, I mean, imagine how few birthday presents you'd get if you lived there. You'll know this in detail when we get to the section of the class on Kepler's laws. But for now, let's go with a simple idea. The Earth's here, goes around Jupiter, 5 times further away, so it's a much bigger circle. And in fact, the reason the planets go around the Sun is they go just fast enough not to fall in. If you've ever thought about it, we are gravitationally bound to the surface of our planet. What that means is we'd fall through if there wasn't a surface here. The Earth is not sitting on a big table. I hope that's not a surprise to anyone. Good. Sometimes you worry with these comments. So the only thing that keeps the Earth from not falling into the Sun is the fact that it's falling just fast enough away from the Sun to keep going in a big circle. For every second, it's pulled to the Sun by gravity, but it's also running away. So if you combine those 2 directions, you end up going in a circle. So that's going constantly. Now Jupiter, 5 times away, is the gravitational pull of the Sun going to be more or less? Less. Good. Because gravity, it's an attractive force. It scales with the mass of the object. That's why we all go around the Sun rather than all going around some random dust grain. And the closer you are to an object, the stronger its gravitational force is. Jupiter, 5 times further away, feels less of a force. So do you think it has to go faster or slower to stay at its radius? Very good. Slower. So it's going slower, and it's got a much bigger radius. So we know it's going to take more than a year to go around the Sun. It'll take roughly 10 years. The amount of time it takes light to get here from the nearest star. Anyone have a guess as to what this is? 4 years. Excellent. Who said 1 billion? Okay, it's good to guess. It's good to get a wide range of answers. That's perfectly fine. 1 billion is a lot, though. If it took 1 billion years for light to get here from the nearest star, work with me here. If it took 1 billion years for light to get here from the nearest star, how long would it take for light to get here from the furthest star? Longer than the age of the universe. So that would mean that the sky would be mainly dark because there wouldn't have yet had enough time pass for light from most objects to reach us. We would look out at night and we'd go, wow, clear sky tonight. It's great. I see both stars. That doesn't happen. So that tells us that light travels faster than that. And 4 years is in fact correct. The light from the nearest star system, the Alpha Centauri system, takes 4 years to get here. How about the amount of time it takes light to get from the Sun to the Earth? Will that be bigger or smaller than 4 years? Smaller. Will it be a little bit smaller or a lot? A lot. Anyone know what it is? Excellent. 8 minutes. So that means if a sunspot bursts out on the Sun, it takes 8 minutes for us to see it. There's a phase lag in the information. Has anyone ever seen the film 2001? Space Odyssey. There's one little scene in it where a man is traveling, a business traveler, and he goes up to the moon, and then he calls his daughter back on Earth. And if you've noticed, he says, "Hello, how are you?" "Oh, I'm fine." There's a gap. What's he waiting for? He's waiting for the signal to go from the moon down to the Earth, and for his daughter to hear it, say something, and bring it back. So there's a 1 second phase lag between the Earth and the moon. There's an 8-minute phase lag between the Earth and the Sun. There's a 4-year phase lag between the Earth and the Sun and the next star system. So imagine if we sent a colony out there and then we started chatting. You'd send a message and it would be 8 years to get an answer. Distance education really wouldn't work. What are these 4 things? We got 8 minutes, we got 1 year, 4 years, 10 years. So I say the winner, the longest time is what? So this is interesting because that tells us that we've sort of mixed timescales. The timescale for action within the solar system is 1 to 10 years. And the timescale for light to travel from the nearest stars is also 1 to 10 years. So they're on a similar scale. One is not dramatically smaller than the other. Let's pick up our next group. We're going to look at the next 4 shortest times. The death of a star, a human life, the amount it takes light to travel from another galaxy, not the nearest star, but the nearest galaxy, and the epoch of human beings, how long human beings have existed on this planet. Well, again, look at those 4 and sort them in time. And if you get through that, estimate the length of each one. Let's take some guesses. Life of a human, Milky Way to Andromeda, light, epoch of us. Fourth is death of a star. So Daniel's group would put the epoch of human beings shorter than the amount of time it takes light to travel from the Milky Way. All right, let's walk through these four. So we're starting with a time scale of 100 years, which I think personally is a really big clue. What do we think that is? Human life, yes. Then we pick up with the amount of time that human beings have been here. That's roughly 500,000 years. What do we think is a million years? So we'll take votes. What we have left is the amount of time it takes light to get to us from the Milky Way and the amount of time it takes for a star to die. Hands for the Death Star. Wow. Hands for the time for light to get to it from Andromeda. Interesting. Okay, very good. It's about 1,000,000 years for light to go from the nearest galaxy to us. So that means the phase lag of information that we have, 1,000,000 years for the nearest galaxy, billion years, 10 billion years for the furthest galaxies away from us. And then our final number here is the death of the star. So that's quite extended. Stars actually live the same way that humans do, in the sense that you run around jogging for 100 years, turning in your homework on time, and then you get a heart attack and you die very quickly relative to your whole lifetime. Same with a star. It jogs around doing its homework for 10 billion years, and then it dies. And even though from a star's perspective, that's a really fast process, if your total life is 10 billion years rather than 100 years, those death throes are pretty long. Let's pick it up with the next set of objects. This time we're looking at the last five. The age of the universe, the lifetime of a star, which I think I just gave away, the great dinosaur extinction, how long ago was that in the past, the amount of time it takes light from a distant object like a quasar to come to us. A quasar is an unusual object. It is as big as a star, but it's as bright as an entire galaxy. And then the amount of time it takes the sun to go around the Milky Way once. Let's sort those five from shortest to longest, and then try and figure out how you might use a telescope to estimate the length of each one. Okay, let's pick up with our lists. Who actually knows when the dinosaurs went extinct? 65 million years ago. So what's the next thing on our list? Death to the dinosaurs. Does everybody agree that's the first thing, the shortest thing on our list? 65 million years. It's the exact number we've got up on the screen here, so that's a good bet. What do we think's next? What is a time scale of 100 million years? The Milky Way go around the galaxy? Any other guesses? Life of a star. That's really short for a star, so that would have to be an extremely massive star. A typical star lives about 10 billion years. They really, they get on in middle age. So this is still a very short time scale. And in fact, that's just under the time for the sun to go once around the galaxy, 100 million years. So it takes us a year to go around our star. It takes our star 100 million years to go around the galaxy. That's how much bigger the galaxy is than a star. Next on our list, we're looking at 1 billion years. That's a very conservative estimate of the life of a star, so that's on the short end. Then we have the amount of time it takes light to come from a quasar to here. A quasar, as I explained to a couple groups, is an object found early in the evolution of the universe. So we have to look halfway across the universe in order to find one. And so it takes billions of years for that light to come here. And then finally, 14 billion years. Does that number resonate with anyone? Life of the universe. That's roughly the age of our entire universe. So just as I said everything you found in space was contained within our universe, everything contained within time is in the age of the universe.
I want to close by emphasizing two key points about today's material. My first point is that the universe is vast, and when we study it, we focus on both extremely small and extremely large size and timescales. To understand the universe, we must understand the behavior of atoms, because much of the light that we see from celestial objects comes from photons which are being absorbed and emitted by individual atoms, and these atomic transitions can take place on timescales of small fractions of a second. We must also comprehend the evolution of gigantic structures in the universe, like the superclusters formed by thousands of galaxies and the great empty voids which lie between them. And we must study the evolution of matter over the entire age of the universe, spanning 14 billion years. Not only are the planets, stars, and galaxies evolving with time, the universe itself is expanding outward, growing ever larger with time. So we have to stay on our toes to keep up with it. My second key point is that there is an absolute speed limit in the universe, one which bounds all matter and all light. Nothing travels faster than the speed of light, 3 times 10 to the 5th kilometers per second. A direct result of this limit is the fact that when we observe distant objects, like quasars and the most distant galaxies, we see them not as they are today, but as they were at the dawn of time, when the photons that are captured by our telescopes first left them to traverse across the universe. Telescopes are most marvelous time machines.